So now we are going to introduce a new class of LDPC codes called irregular LDPC codes. And these irregular LDPC codes, they improve upon LDPC codes in multiple respects. So far we have seen that regular LDPC codes perform quite well, at least on the binary erasure channel, and we saw that we should select a variable node degree of 3 to get the best possible performance. But we see that there is still a considerable gap to capacity. So we know that the threshold for a 3.6 LDPC code has a threshold of epsilon star equals 0.4292 approximately. So this is the largest epsilon at which an optimal code can decode. But we also know that the capacity of the binary erasure channel is in this case 0.5. And there is a discrepancy between these two numbers, and this discrepancy is what we're going to close. So how do we do this? Well, we need to generalize the construction. That's a very useful tool in engineering. If you have a construction that is specific in some sense, then we need to relax a little bit the design rates, so to allow more degrees of freedom. We need to insert new degrees of freedom that we can then optimize. So what we're going to do is we relax the constraint that the variable node and the check node degrees must be regular. That's essentially what is called an irregular LDPC code. So we have an irregular LDPC code, and an irregular LDPC code is essentially an LDPC code where the number of ones in each column is not necessarily constant, and the number of ones in each row is also not necessarily constant. Essentially, it's a generalization of the construction that we have seen before. So how does this generalization work? Well, let's take a look, and we start by looking at something called the degree distribution. That's how we can specify these LDPC codes. So the degree distribution essentially is a very elegant and convenient way to describe irregular LDPC codes using polynomials. So we start with just counting what we have. So we have a parity-check matrix or a tenor graph, and we start by counting or by looking at the variable nodes. And we look at the degrees of the variable nodes, and we define the number of variable nodes of degree j to be equal to capital lambda j. So essentially, this is a variable node that has j connected edges. We denote it by capital lambda j. And we do the same thing for the check nodes. So we denote the number of check nodes of degree j by capital pj, capital rho j. So essentially, it's just counting the columns in the parity check matrix of a certain weight, or counting the rows of the parity check matrix of a certain weight. This is the same as counting the rows or the degrees of the variable node and check nodes. And we're going to see an example very soon. So if we have now a code that has length n, then of course the sum of all the degrees must be equal to n. I mean, if we count all the variable nodes, the total number of variable nodes is n, so the sum of all these lambda j's must be equal to n. Very similarly, the sum of all pj's must be equal to m, which is the number of check nodes. Now, check nodes is exactly 1 minus the design rate. And then we count the number of edges. So what is the number of edges? So we have lambda j variable nodes of degree j, and each of those variable nodes has j edges. So the number of edges in the tenor graph is j times lambda j summed up over all possible j. That's when we count from the variable node side. We look at the variable nodes, we go to each variable node, we first count the number of variable nodes of degree j. The ones that have j connected edges, We multiply those by j, and then we get the sum of all the edges. So this is the number of edges from the variable node side, and we can do the same thing coming from the other side, from the check nodes. And from the check nodes, we have pj check nodes of degree j. They have j connected edges. So sum of all j times pj is also the number of edges, and this then must be equal to the sum of all j times lambda j. This is another condition that this degree distribution needs to fulfill. So let's take a look at an example. So we can take a look at the Hamming code. The Hamming code is a perfect example of an irregular code. And we can just start counting for the Hamming code. So in the Hamming code, we have 3 variable nodes, v5, v6, and v7, that are of degree 1. So lambda 1 is equal to 3. Then we have 3 variable nodes, the blue ones, v2, v3, and v4, that are of degree 2. So we can see they have 2 connected edges. So we have a degree 2. And therefore, lambda 2 is equal to 3. Then we have one single variable node, that's the red one. It has 3 connected edges, so it has degree 3. So lambda 3 is equal to 1. Then we have no variable nodes with degree 4, no variable nodes with degree 5, and so on. So lambda 4 is equal to lambda 5 is equal to 0. Then we have 3 check nodes in our code. The 3 check nodes have all degree 4. Count 4 connected edges for each of those. So we have P4 is equal to 3. And all the other P's are equal to 0 because we have no connected edges. So we can count the number of edges, E. We know this is J times capital lambda J. So this is 1 times lambda 1 plus 2 times lambda 2 plus 3 times lambda 3. So this is 3 plus 6 plus 3. And this is 12. And we can verify that we have 12 edges. This is also the sum of j times pj. So 3 times 4 equals 12. Okay, so this is an example of an irregular code, and this is a way how we can describe this irregular code. So it can be very convenient to introduce a polynomial notation. And this polynomial notation is given as follows. So we define a polynomial lambda of z. Polynomial lambda of z is the sum over all j of lambda j times z to the power j. Z is just a variable that we introduce and to give it a polynomial. Similarly, we define p of z. So p of z is the polynomial over all j, pj times z to the power j. So let's define these polynomials for the Hamming code that we had on the previous slide. So I can just copy the tenor graph on the next slide so that I can that we can just see it. So let me paste the tenor graph here and put it a bit smaller, put it up in the corner so that you can verify what I'm talking about. So we start with the, we look at this for the Hamming code. And we have the following situation. We have the polynomial lambda of z is equal to lambda 1 times z to the power 1 plus lambda 2 times z squared plus capital lambda 3 times z cubed. And this is equal to 3 times z plus 3 times z squared plus z cube. Similarly, we can say that P of Z is equal to 3 times Z power 4, because we have 3 check nodes of degree 4. So now we can count the number of edges. We did this already in the previous slide. We're just going to repeat it. We have the number of edges. Moment. So E is equal to 1 times lambda 1 plus 2 times lambda 2 plus 3 times capital lambda 3, which is equal to 1 times P1 plus 2 times P2 plus 3 times P3 plus 4 times P4, and so on. So now we can express the number of edges also in terms of the polynomials. So this maybe looks already a little bit familiar, this expression. We relate this to a polynomial. So how can we relate this to the polynomial? And that's we can do it the following way. So what we see, so if we look at the derivative of the polynomial, so lambda prime of Z, that is the sum from J going from 1 to dv max. So this is the maximum variable node degree of J times capital lambda J times Z to the power J minus 1. Standard derivative of a polynomial. And we see that P prime of Z, again, equal to the sum from J equals 1 to dc max, J times Pj times Z to the power J minus 1. So now we can express the number of edges also in terms of the polynomial. So the number of edges is given by lambda prime of 1. Just by, you see this by comparison. So if you insert Z equals 1, you get the sum of J times lambda J. So it's this polynomial lambda of Z. You take the derivative of this polynomial and you insert Z equals 1, and then you get the number of edges. Or this is equal to P prime of 1. Polynomial also has another advantage. You can express the rate as a function of the polynomial. The rate Rd is equal to 1 minus, the design rate is 1 minus m over n. What is m? M is the number of variable nodes. What is the number of variable nodes? So it's just the sum over pj. This is 1 minus the sum over j times pj divided by the sum over j times capital lambda j. How do we get pj and lambda j from the polynomial? Well, this is also easy. So this is 1 minus p of 1 divided by capital lambda of 1. So we insert 1 in the polynomial and you get the number of variable nodes or check nodes respectively. So these polynomials are a very convenient way of handling those irregular codes and describing their properties. So let's take a further look. So here we summarize the properties. We have the following relationships from these polynomials. So lambda 1 is equal to n, lambda p1 is equal to m. The rate is 1 minus p1 divided by lambda 1, and the number of edges is lambda prime of 1, and this must be equal to p prime of 1, so this number of edges. So how are these polynomials lambda and p called? They are called the degree distributions from a node perspective. So now, very often, we are interested in the performance of an LDPC code, but we don't care about the length n of the code. So, and then it is more convenient to use normalized degree distributions. So if you want to compare codes of different sizes, then we need normalized degree distributions. So we have L of Z, that's lambda of Z divided by N. So we take we look at the fraction of degrees of variable nodes of a certain degree. And we look at the fraction of check nodes of a certain degree. Recall, this is equal to lambda Z divided by N. And this is equal to PZ divided by M. M is equal to P1 and N is equal to lambda 1. So these are the degree distributions, the normalized degree distributions. And here we have another example. So we saw that the check nodes, they have a degree of 4. And we can now have normalized degree distributions, which we call R of Z and L of Z. So why is it called L of Z and R of Z? L because these are on the left of the tenor graph, and R because the check nodes are on the right. That's the idea of how we can remember this. So we have 3 check nodes of degree 4. So R of Z is 3 divided by the number of check nodes. So it's essentially all 100% of the check nodes of degree 4. So if Z to the power 4 is R of Z. So starting from lambda of Z, we normalize by the number of variable nodes, which is 7. That gives us L of Z. So it's 3 out of the 7 variable nodes of degree 1, 3 out of 7 variable nodes of degree 2, and 3 out of 7 variable nodes of degree 3. So that's how we can get the normalized degree distribution from a node perspective that is called L of Z. So these are the, here you can see the different colors. Also, this should be clear by now. Okay, so now we introduce something that is slightly different. We introduce the degree distribution from an edge perspective. And that one is going to be a little bit more interesting for the analysis. So we introduce polynomials lambda of Z and rho of Z in the following way. So lambda of Z and rho of Z are essentially L prime of Z, so the derivative of the polynomial L of Z divided by the derivative evaluated at position for Z equals 1. And because of the normalization factors canceling out, this is the same as lambda prime of Z divided by lambda prime of 1. And we define this polynomial, now we define it slightly differently. So this is the sum over all I of lambda I times Z to the power I minus 1. That's the minus 1 comes from the fact that we take a derivative here. So minus 1. Same thing for rho of Z. This is the sum of all I, rho I times Z to the power I minus 1. P prime of Z divided by P prime of 1 is equal to R prime of Z divided by R prime of 1. So what are these lambdas and rhos? And that's a very interesting observation here is that lambda prime of Z, lambda I and P and rho I, they correspond to the fraction of edges that connect to variable nodes of degree I. So if you have a certain lambda 2, for instance, that's the fraction of edges. So we count all the edges and to look at how many edges connect to a variable node of degree 2. And that's lambda 2. So how can we see this? Well, we start from the total number of edges. The total number of edges is the sum of I times lambda I, which is equal to lambda prime of 1. This guy. So what is the number of edges that connect to variable nodes of degree I? That is I times lambda I, because we have capital lambda I variable nodes of degree I, and each of those has I edges, so it's I times lambda I. So now we have I times lambda I. We take the derivative of lambda prime. So lambda prime of z is again sum from j from 1 to dv max. J times capital lambda j times z to the power j minus 1. So I times lambda I corresponds to the coefficient of z to the power I minus 1 of the derivative of lambda prime of z. So if we define lambda of z in this way, that means that lambda I is equal to I times lambda I divided by the total number of edges. So lambda I is the fraction of edges connecting to variable nodes of degree I. And we can get very similar expression for rho I. So then we use L of z, then we get the normalized expressions directly, or if we insert P prime of z, R prime of z, then we go for rho I. So let's take a look at an example. Here is we start with the example. So here is the example. We have E equals 12 edges, and all 12 edges are connected to check nodes of degree 4. So P of rho of z is equal to z cube. We have a cube because we have I minus 1. So this tells us all edges are connected to check nodes of degree 4. So now we have, out of these 12 edges, we have 3 edges, the red ones, that are connected to variable nodes of degree 3. So 3 out of 12 is 1/4. So we have 1/4 z squared. Squared because we have power I minus 1. So 3 degree 3 corresponds to polynomial z squared. Then we have 6 out of the 12 edges. They are connected to variable nodes of degree 2. So these are these blue edges. So what we see is, we count the edges. 6 out of the 12 connected to variable nodes of degree 2. 6 divided by 12 is equal to 1/2. So we have a lambda 2 of 1/2, and it is assigned with the indeterminate z. Degree 2 means exponent 1. Then we have 3 out of the 12 edges that are connected to variable nodes of degree 1. 3 out of 12 is 1/4. So we have 1/4 of the edges connected to degree 1. So it is z to the power 0. Z to the power 0 is equal to 1. So we see that lambda of z is equal to lambda 1 plus lambda 2z plus lambda 3z squared. Okay, so these are the degree distributions from an edge perspective. So let's go back. So these are the degree distributions from an edge perspective. So this is very important. And these are essentially the ones that we are going to use later. These are the edge perspective. Okay, so we can find a relationship of calculating between node perspective and edge perspective. So they are very nice relationships. So you can transform these degree distributions. And that's the following ones. So we have L of z. L of z is equal to lambda of z divided by n, or lambda of 1. And L of z can be expressed as the integral over lambda tau d tau from 0 to z divided by the integral from 0 to 1 of lambda tau d tau. Essentially, we know that lambda is the derivative of L. So L is then the integral of lambda. And then we just need to normalize accordingly, and that's given by done by the denominator. Same for R of z. R of z is P of z divided by m, or n minus 1 minus the design rate. That's the integral from 0 to z of rho of tau d tau, an integral from 0 to 1 divided by the integral from 0 to 1 of rho of tau d tau. Now we can also calculate the average variable node and check node degrees, which is dv average. dv average is L prime of 1. It's the fraction of variable nodes of a certain degree times this degree. It's just given by L prime of 1. So L prime of 1 is essentially, we can go into, take a look at this equation. L prime of 1, if we take the derivative of the numerator, that's going to be just L of z. If we insert 1, we get 1. Divided by this constant, so this is 1 divided by this normalization constant. So you see, the numerator will be this. This will be equal to 1, and then we have the normalization constant. Same thing for the average check node degree. So let me mark this. This is a quite important formula. The average check node degree is r prime of 1, or 1 divided by the integral from 0 to 1 of O of tau d tau. And then we can use this average variable node and check node degrees to express the design rate as well. So this design rate is 1 minus the average variable node degree divided by the average check node degree. And we can just insert our values, and this is how you can express the average design rate as a fraction of, or as a function of, the degree distributions from an edge perspective using this integral. So let's take a look at what this means in particular. So we have the design rate, or how we get there. So we have the design rate RD is equal to 1 minus m over n. So what is m? M is the number of edges divided by the average check node degree. So we can also say the number of edges is the number of variable nodes. So this is equal to saying E is the number of check nodes, M times the average check node degree. So that's how you can express M and E as a function of the average degrees. Same thing for the number of variable nodes. Number of variable nodes, N, is the total number of edges divided by the average variable node degree. Okay, so now we can express the design rate, RD, is equal to 1 minus, now we insert. So we insert M and N. So we have E divided by the average check node degree divided by N. So it's E, the average variable node degree. Fortunately, the E cancels. So this is 1 minus the average variable node degree divided by the average check node degree. That's how we get to this expression. So now we look at the average variable node degree, dv average. So it's the sum from j equals 1 to the maximum variable node degree of j times lj. The fraction of variable nodes of a certain degree times the degree j. So it's essentially the expectation of L. And we see that this is equal to L prime of 1. So now we have L of z is equal to the integral from 0 to z of lambda tau d tau divided by the integral from 0 to 1 of lambda tau d tau. Then now we just take the derivative, so we apply Leibniz formula. So we have L prime of z. The denominator is a constant, does not depend on z, so we can just write the denominator, integral from 0 to 1 of lambda tau d tau. So if we take a look at the numerator, we need to calculate the numerator, and in order to do so, we need to take the derivative of integral. So we need to calculate essentially the derivative with respect to z of the integral from 0 to z of lambda tau d tau. And in order to do this, we can use Leibniz integral rule. And let me paste it for you. So this is Leibniz integral rule. So in order to have the derivative, and let me copy the rule up here so that we have it ready at hand. And here we go. So in order to take the derivative, we first need to take the function itself with respect to the and take the derivative of the upper limit of the integral. Then we need to subtract the function evaluated at the lower limit of the integral times the derivative with respect to the lower limit of the integral. And then we need to derive the function with respect to the variable. So let's do this. We do a small side calculation over here. We calculate d with respect to dz equal from 0 to z of lambda tau. Or let's do it over here. That should be sufficient space. Lambda tau d tau. So we start with the function evaluated at the upper limit. So this is lambda of z times the derivative of the upper limit with respect to z is equal to 1, plus the function evaluated at the lower limit, lambda of 0, times the derivative evaluated of the lower limit with respect to z. This is a constant. Derivative of a constant is equal to 0. Plus the integral from 0 to z times the derivative of f of tau d tau. So now the function f of tau doesn't depend on z. So this is a function that depends on tau. But we take the derivative with respect to z. So with respect to z, this function is a constant. So the derivative of this guy is equal to 0. So we end up with lambda of z. So what we can do is we can replace the numerator of this expression by lambda of z. Okay, so now we have L prime of z, but we are interested in L prime of 1 because that gives us dV average. So how do we get L prime of 1? We just insert 1. So it means we get L prime of 1. This is equal to lambda of 1 divided by the integral from 0 to 1 of lambda tau d tau. This is equal to lambda 1 is nothing else as the sum from 1 to dV max of lambda I divided by the integral from 0 to 1 of lambda tau d tau. And we know the lambda i's, they are fractions. The sum over all the fraction is equal to 1. So this is equal to 1 divided by the integral from lambda tau d tau evaluated between 0 and 1, which is what we wanted to prove. So we have finished the first part of the proof. The second part is works the same. We just need to replace L with R, and then we can calculate DC average, which is the same expression. Then we get R prime of 1, and then after some steps, we get the integral 1 divided by the integral from 0 to 1 of rho of tau. Let me rewrite it again properly. So this is 1 divided by the integral from 0 to 1 of rho of tau d tau. So that concludes this proof and this derivation of the average variable node and the average check node degrees. With this is our example. Now we can recall what happens when we analyze LDPC codes. So when we analyze LDPC codes, we take a look at the decoder. So and inside the decoder, each edge gets updated separately. So the decoder, we go to all the nodes, and then inside each node, we go to all the edges. And then we calculate the probability that a certain edge is erased. So when we looked at a variable node of degree j, the probability that an outgoing message corresponds to one edge is erased is given by epsilon times chi to the power j minus 1. That's the same expression we had for regular LDPC code. Now we have a fraction lambda j of edges that are of degree j. Fraction lambda j of the outgoing messages are erased with this probability. So this is the probability for the messages of degree j, and we have a fraction of lambda j times those messages. So probability that the fraction lambda j of outgoing messages is erased, and these are of degree j, is lambda j times epsilon to the power chi j minus 1, or we take everything that does not depend on j, put it in front. So it's epsilon times lambda j times chi to the power j minus 1. So in total, we have j degrees, so we can calculate the probability that an outgoing message is erased. So we take the average over all possible degrees. So it's the sum from j to dv max, lambda j times epsilon times chi to the power j minus 1. We take epsilon, move it in front of the sum. So it's epsilon times the sum over j of lambda j times chi to the power j minus 1. And this looks fairly known. This looks just like, let me go back. This looks just like our lambda of z, but not evaluated at z, but evaluated at chi. So this is equal to epsilon times lambda evaluated at chi. So we get the probability that an outgoing message is erased, xi, is equal to epsilon times lambda of chi. Okay, half of the analysis is done. So now we look at the check nodes. So each edge of a check node is updated separately. And now we look at the probability that the outgoing message of a check node of degree j is erased. So an outgoing message of degree j is erased with probability 1 minus xi to the power j minus 1. This is what we had for regular codes. Now again, we have a fraction rho j of the edges of degree j. So we have chi is equal to the sum of from j going to dc max, rho j times 1 minus xi to the power j minus 1. This we can also insert this, or we can factor out, we can multiply. So this is the sum over all j of rho j. Rho j is a fraction of edges, so if you sum up over all the fractions, we get 1. So this is 1 minus the sum over all rho j times 1 minus xi to the power j minus 1. And this is then finally, this is 1 minus rho evaluated at 1 minus xi. So now we have also an expression of chi as a function of xi, including rho. So now we can put again everything together, just as we did for regular codes, and we get the following. So we have the following update equation for the variable nodes. Xi L is equal to epsilon times lambda of chi L. And chi L is 1 minus rho of 1 minus CL. So now we have an iterative update equation for irregular LDPC codes. An irregular code with variable node degree distribution from edge perspective given by lambda of z, check node degree distribution given by rho of z, and we have the iterative update equation that is given as follows. So CL is equal to epsilon times lambda of 1 minus rho 1 minus CL minus 1. Looks very similar, but now instead of having the exponents, we have more generalized polynomials. And again, we start with C0 being equal to 1. Okay, so this is our iterative update equation, and that's how we can analyze irregular LDPC codes. So now we're going to look at some irregular LDPC codes, and we're going to see the performance of those irregular LDPC codes. So let's take a look, and we have regular LDPC codes. We can put them also in this framework. So for regular LDPC code, we have lambda of z is equal to z power dv minus 1, and rho of z is equal to z power dc minus 1. And this is just one code. And now we take a look at an irregular code. And here is an example of an irregular code. And this is some lambda of z, and this is rho of z. So this kind of falls out of nowhere. And you have to trust me that I just invented this code, and it's a pretty solid and good code. But it still has been invented. So it's you have to believe me that these coefficients make sense. We'll later see how to find these coefficients. So these are some lambda of z, rho of z, and now we can do some calculations. And we can calculate the average check node degree. So it's the integral of rho of tau d tau. And these are all polynomials, so the integrals are fairly easy. So it's 0.5 times z power 8 divided by 8 plus 0.5 times z power 9 divided by 9. We insert 1 and 0. And so this is equal to 0.5 divided by 8 plus 0.5 divided by 9. Inverse, and we get 8.47. So that's the average check node degree. We can do the same for the average variable node degree. This is a little bit more nasty. You probably like to do this using a calculator or computer algebra program. But we find an average variable node degree of 4.235. We can also calculate the design rate. Again, it's 1 minus the fraction of these integrals. Insert 1 minus dv average over dc average. And we find that the design rate is equal to almost 0.5, very close to 0.5. So we can also give the variable node degree distribution from node perspective. That's the one you need if you want to construct the code. So again, you find this by taking the integral and normalizing it. Again, it's a little bit nasty because this is what you need to insert, but you find there's values for L of Z. And with this, we can go ahead. We can calculate R of Z. So we see that 52% of the check nodes have degree 8 and 47% of the check nodes have degree 9. Here we had 22.5% of the variable nodes of degree 2, 68.7% of variable nodes of degree 3, 0.4% of degree 11, and 8.4% of degree 20. So here is an example tenor graph that you see in the back. We plot it for n equals 80. And you can see that here we have variable nodes of degree 2, if you look closely. Here we have variable nodes of degree 3, if you look closely. And here we have variable nodes of the higher degrees, so 11 and 20. And if you count the check node degrees, you see you have 8 and you have 9 degree 9 check nodes. How we can construct such a code, that is also something that we're going to look a little bit later. But this is an example tenor graph of such a code. It's a bit messy, but it's a typical irregular LDPC code. And again, it's rotated by 90 degrees, so the variable nodes are on top and the check nodes are on the bottom. So now we can also define a decoding threshold. So the decoding threshold of is associated with an irregular LDPC code. It has degree distribution lambda of z and rho of z, and that's a threshold that is given by epsilon star. So epsilon star, that depends on lambda of z and rho of z, again, is the largest epsilon, such that this update equation CL converges to 0 if C0 is equal to 1. So that's the threshold of the code. And alternatively, we have a fixed point characterization. So epsilon star, that's the largest epsilon, such that this fixed point equation, xi is equal to f of epsilon xi, has no solution in 0 and 1. We don't look at the trivial fixed point, we exclude the trivial fixed point. So it has no solution in 0 and 1, or it's the smallest epsilon such that we have a fixed point. We look at all the epsilons that have a fixed point. The smallest one is the one where it barely doesn't work, and if we go a tiny bit smaller, then we will converge. But again, very same reasoning as for regular codes. And again, the update equation is epsilon times lambda of 1 minus rho of 1 minus c. So let's take a look at this, how this works. We have this irregular code, and we see that for 0.48, update equation doesn't work. So here we show CL as the function of the iteration L. So the update equation doesn't work for epsilon equals 0.48. But if you decrease it a tiny bit, so for instance, for epsilon equals 0.47, you see that it steadily decreases. There are two jumps where it decreases more rapidly, but after 500 iterations, we have reached 0. If we decrease epsilon further to 0.47, we converge significantly faster. And we call that epsilon star of the 3.6 LDPC code was equal to 0.4292. So we have quite a significant improvement compared to the 3.6 code, and already at 0.47, epsilon equals 0.47, we converge quite rapidly. So pretty nice result and pretty good code. So this is the fixed point characterization. So as a function of xi, we plot f of epsilon xi minus xi. We know if this curve is below 0, so it's 0 everywhere except at the fixed point equals 0, then the code will converge. And we see we have very aesthetically pleasing curves here. We see that the code will not converge for epsilon equals 0.7, where we now actually have 4 fixed points. So, but then if we increase the threshold to 0.47, decrease epsilon to 0.4739, we are barely below this curve and will converge. So it has a threshold of at least exactly epsilon equals 0.4739. Okay, so very nice. We have improved significantly. Now we look at another code, because you may say, okay, this is not fair because the average variable node degrees and the average check node degrees were different than for the 3.6 code. So now we take a look at a code where we actually take the same average variable node degree and check node degrees than the 3.6 code. So that's this irregular code. We have a second example. So now we have lambda of z given by this guy, rho of z given by this guy. So actually we see that the check node degree is regular. This is the code that has a regular check node degree DC equals 6. And I encourage you to verify the design rate. So insert the numbers, do the number crunching, calculate the integrals, and you will get a design rate of 1/2. Also, I encourage you to calculate by hand the average variable knot degree. You find it has an average variable knot degree of 3 and a check knot degree of 6. So it is very similar than the 3.6 regular LDPC code. And this code even has a better threshold. It has a threshold that is equal to 0.4809. And I encourage you also to take either do a Python script or a MATLAB script to calculate and verify this threshold. So we have done it for regular codes and do it for irregular codes pretty easily, just using some polynomial evaluation. Here is the fixed point characterization. We see that for epsilon equals 0.48, we have fixed points here and here. So it doesn't converge. But if you go to 0.4809, we see that here we barely touch the zero curve. So actually we don't touch it. So we are below 0. And this means we can actually converge with this code. And here are the exit charts of this code. So this is for epsilon equals 0.48. So we see that the curves just touch. We have a tiny, tiny decoding tunnel. We also see that we need quite a lot of iterations to go to this tiny tunnel. And if we just decrease epsilon a little bit, we decrease epsilon to 0.47, then we see that the tunnel is nicely open and we can converge using quite a lot of iterations, but eventually we will converge. So these are the exit charts of this irregular code. And you can calculate the exit charts in a very similar way than for regular codes. It's just, again, averaging over the degree distribution. So with this, we close this video. And now in the next video, we're going to prepare how to optimize lambda offset and rho offset. And to do this, we'll first need a little bit of theoretical background.